Okay, I will probably start now. And I'm very thankful to Rachid for the introduction. And especially it matches very well what I'm going to tell, fits perfectly to what Rachid has presented just now. And in some sense, what I'm going to talk about is a slightly different perspective on distributed computations, in which you try, instead of trying to focus on a specific execution, like in the proof of the impossibility of consensus, where you try to identify a specific execution in which some properties of the problem are violated. For example, you cannot decide on a value, because if you decide on a value, you might violate consistency. So here, you try to visualize the whole scope of executions of a given model. And then you model it as a structure. It's a combinatorial structure. You talk about combinatorial topology because you work in discrete space. Computing is about discrete structures. And it's what we call a simplicial complex. It's an object which you can embed in space. And by reasoning about the properties of this object, you can somehow deduce what is possible and what is not possible in a model of computation. And distributed computations are all about uncertainty and indistinguishability. So you cannot, by looking at your local view, you cannot decide what other processes see. And sometimes it's critical because you cannot know what output to produce. And this perspective is actually what I tried to use here as an image. It's like it's a philosophical debate about the atomistic approach to the world versus holistic. Like in our context, it's combinatorial versus operational. Whether you look at the executions, how they unfold in time, or you try to model all executions as an object and try to look at the object. And just to give you a little bit of flavor, in general, in this talk, I'm going to do a lot of shortcuts and hand waving because the topic is very rich, and I don't have, unfortunately, enough time to show you the richness of it, but I will try to give some hints about how it looks like. And just to give you a little flavor, let's recall what is crucial for a process to know about the distributed system. Usually, you look at the view of a process. So it's just its local state, which depends on the actions the process took during the computation, but it cannot know for sure which states other processes have. Sometimes it can. So this is what we call a local view. Yeah. And we model it as a point in space, just a point. And it's colored. And the color is a process identifier, typically. So in this case, we use process P0, and we color all the views of process P0 with the color red. And we also put a label, which somehow denotes the view the process has. Okay? And then some views can be compatible with different states of the system. Yeah, for example, we can have a state in which P0 has view 0, and, well, sorry, this is a typo, P1 has a state 1. And we model this global state of the system of two processes as an interval. So we connect the vertices corresponding to these two local views with an edge. Okay, this is what we call a one-dimensional simplex. Yeah. So there is a state in which these two guys have these local views. Okay, so far so good. So now we're slowly coming to the notion of indistinguishability. So when a single local view is compatible with multiple global states. Yeah. And this is what we model as a complex. Well, we'll come back to these notions in detail a little bit later. But for now, we have a system of two processes, and we have 4 different states. Yeah, and in each state, we have, process 0 having some view and process 1 having another view. And this corresponds to the situation where some input configuration of the system allows processes to pick up inputs from the binary set, 0 or 1. Yeah, so respectively, every process has 2 possible local views. And altogether, we have 4 combinations. Okay? So this is a complex, sorry? Yeah, so you have two vertices of red color. So the color here is a process identifier. Yeah, so we have P0 having 0 and P0 having 1. Yeah, so but of course you cannot connect this with an edge because you cannot have in the same system state a given process having 2 different views. Okay, So this is just, so here we already have captured some uncertainty. Yeah, so the process has some input, but it doesn't know the input of the other process. So it's compatible with two states. Okay. And this is what we call one-dimensional complex, and one-dimensional because we can embed every simplex in this complex in a one-dimensional space. Yeah, so it's okay. So now, how we model computations? We model how this structure evolves in time. And for example, we can consider a simple scenario in which processes communicate over a synchronous, reliable channel. So they perfectly communicate all the information they have to the other process. And in this case, the situation is very simple. So what we get after communicating over this channel is something like this. Yeah? For every state here, we have an interval, but there's no ambiguity. All uncertainty is lost. Why? Because they know exactly what the other process has. Yeah? There is exactly one system state to which I belong after I run one round of this communication. Okay, so far so good? So here we have disconnected structure. So it's still a complex, yeah? So every element of this complex is a simplex, a one-dimensional simplex. So, and the labels here is all the information they have. So they have exactly, so here it's a vector of inputs. Yeah, so everybody knows everybody's input. Okay? Unfortunately, well, as we know already, this actual distributed systems are not that good. So they are asynchronous, and sometimes they are fault-prone. So that is why people think about weight-free algorithms, so algorithms in which you are supposed to make progress regardless of the other processes. Yeah, this is important because other processes can be faulty. And the system is asynchronous, so nobody controls. So there is a scheduler which defines who takes step at what time. Yeah, and you don't control it. And it's very hard to devise algorithms for this setting. And this is exactly the setting we are going to consider. But before I go to this, let's take a little bit, like a very short primer in combinatorial topology. Okay, so the notions of combinatorial topologies, well, we're not going to have anything like this. Yeah, combinatorics, computing is much simpler than Klein-Bottle or Möbius stripe. So we have much simpler structures, which are usually called subdivisions. So simplicial complexes which are subdivided of other simplicial complexes. So simplex, well, as I said, we have zero simplex, which is zero-dimensional simplex, is just a vertex. An interval here, it's one-dimensional simplex. A triangle, solid triangle, is a two-dimensional simplex. It has three vertices. 4 vertices, we get a tetrahedron, like a pyramid. It's a three-dimensional simplex. So the dimension here is the number of elements in the simplex minus 1. Okay? So it's intuitively, it's a minimal dimension of a space in which you can embed this, geometrically embed this simplex. Okay? So there are two views of simplices. One combinatorial is just a set of vertices, yeah, no more than that. Just take any set of elements. You have n-dimensional simplex for n plus 1 elements. Yeah. The geometric view is more interesting because you sort of represent it visually in some Euclidean space as a convex hull of linearly independent points. So if you take like 3 points, you need to embed it in a two-dimensional space. Yeah, otherwise you cannot linearly make it linearly independent. Okay. Okay, so once we have this geometrical representation of a simplex, or then of a complex also, so we have simplicial complexes. We can model complexes as collections of simplices, which are closed under inclusion. So every subset of a simplex is also an element of the complex. Yeah. Geometrically, it's like, well, for example, if you have this complex, it's two simplices, A, B, C, B, C, D, and plus all the subsets of these two simplices. This is my complex. This is my combinatorial representation of the complex. Geometrically, it's this. Yeah, so you have A, B, C, and this is B, C, D. Yeah, so you have two connected simplices. Okay. So this is just a set of geometric simplices closed under intersection. What I mean here is that if we have two simplices which intersect in the geometric space, then the intersection should also be a simplex. Yeah. So that's just it makes sense here because yeah, you have two. Let's say, for example, two processes who share states in these two global states for 3 processes. Okay, usually the dimension of a simplex for us corresponds to the number of processes in the system. Yeah. Okay, so far good. So good. And well, once we have the geometric representation of a complex, we can reason about connectivity. And connectivity is one of the most important concepts here because this is exactly what captures uncertainty in the distributed system. Okay. So we all know about path connectivity in the graph sense. Yeah, if you have a path between 2 points. Mathematically, we can represent it as an extension of a map of a zero sphere, means the boundary of an interval, to one disk, to the interval itself. So there is, for any 2 points in the complex, we have a path. Okay? And once we have this mathematical representation, we can generalize the notion of connectivity easily. We can say one connectivity, which is sometimes called simple connectivity, simply connected complexes. So if you can extend a one sphere, which is just a circle here, to two disks, which is just a ring, yeah, you can extend it without continuously extend it, then we know that this complex is one connected. And for example, if I take a torus of this kind, yeah, this is not one connected, yeah, because we have a circle which you cannot collapse. Yeah, so you cannot continuously transform it to a point. Okay, and then you can generalize it. You can generalize it to connectivity. To connectivity, you can extend the sphere, two sphere to three disks, like a solid ball. Okay, so this is what we are going to use. Okay, back to computing. So the simplest setting we can consider is two processes communicating using reading and writing in the shared registers. Probably the simplest distributed computing system you can think of. But still quite interesting, as we already know. Some problems, some seemingly simple problems cannot be solved deterministically in these kind of scenarios. Okay, so we have, like in this case, we have a set of processes. They communicate through shared objects. In our case, we take read-write registers. We also had, we talked last time, 2 weeks ago, we talked about atomic snapshots. It's something which you can implement using read-write registers. We also talked about like objects with stronger semantics, like test and set and compare and swap. And we also, I hope we are convinced that these kind of things are computationally stronger than read-write registers. We cannot implement, for example, test and set or compare and swap using read-write registers. So it gives us more power. Okay. And assume we want to solve consensus. Yeah, again, processes start with values and end with values, and every output value should be an input value, and we guarantee that in every state in which two processes decide, they decide the same state, the same value. Okay? So for two processes, it's something like this. You start with, let's say, 0 and 1. This is the most interesting case where you have two different proposals, and they agree on one of the two output states. Yeah, so in our modeling, this is the input state. And these are two disconnected output states, possible after you run this protocol. Okay? Okay, so two processes, two registers. Every process writes to its own register and reads the other. And let's consider just one round of interaction of this kind. Yeah, so every process PI, well, we usually denote them P0 and P1, yeah, just to reflect the inputs of them. Yeah, P0 proposes 0, P1 proposes 1, just for simplicity. So okay, so the first thing the process does, it writes its input in the register, okay? And then it reads the register of the other process. And this is what it read. And this is its new view, okay? Well, operationally, if we consider all the possible executions of this protocol, it's a very simple protocol, write, read. We have three cases. Yeah, first case is P0 reads the value, well, reads the other register before P1 writes to it. Yeah, in this case, P0 read it and didn't find anything in it. Only find some default value. Didn't find the input of the other process. Okay, so this is like this. So if you have a time flow like this, you have process P0 writing, reading, and then only after that, P1 writes and reads. Okay, so this it's atomic register, so I can denote read and write operations in one atomic step. Okay. Well, symmetrically, we have the other case when P1 reads before P0 writes. Yeah, so now P1 is fast. Yeah, it reads the register of P0 before it was updated. Okay? And finally, we have a situation where the two processes run lockstep, in sync. Okay? So they both write, and then they both read. It doesn't really matter how I shift these points around, as long as this holds, that both guys see each other. Okay? So we have three possible executions, and this exactly matches three possible states of the protocol, which I can model as this. So if I start with this initial state, and let's say P0 proposes 0, P1 proposes 1. After one round of this protocol, what I have is this. Yeah? So these are local states. Yeah, P0 may either miss P1 or see P1. Well, symmetrically, P1 can miss P0 or see P0. Okay? So in the middle, we have the execution which we saw before. Both processes see each other. Okay? But we also have these two guys here, these two executions. Yeah? Somehow they connect the endpoints. And this is what creates a problem for consensus, exactly, the connectivity. Okay. So P0 only sees itself here. P1 only sees itself here. And you have a chain of states which connect these two vertices. Okay? And what's important here is that you can run it longer. You can run another round of this protocol. For example, like this. And what you get is a subdivision of each of these three intervals. And the subdivision looks exactly the same. So now it's similar, but except that P0 sees itself, and then maybe after the second round, it sees P1. But it belongs here because it sees that P1 saw P0 in the first round. Yeah, and for example, if P1 ends up here, it knows that P0 missed P1 in the first round. Well, you have more information. Yeah, you run longer, you communicate more, but you still connected. So what you have is still a connected chain of executions. Okay? Well, connectivity, I emphasize connectivity because this is exactly what prevents consensus from being solved. Yeah, so I can move on and longer. So I have more and more fine-grained subdivision of this interval, which, however, remains connected. And this is a fundamental thing. So the protocol complex, the set of states which are reachable by this protocol, represents a subdivision of the original, of the input complex. And one thing we know about the subdivision is that it preserves the geometry of the initial complex. It preserves the geometry, meaning that, for example, it preserves the connectivity properties. If it was connected initially, it remains being connected. And that, as a result, we cannot really solve consensus because the solo runs, well, solo runs here where P0 only sees itself in all rounds, and P1 only sees itself in all rounds, remain being connected through these executions. And that prevents us from decision because if we, by contradiction, assume that we can decide, yeah, we have to either avoid decisions in some executions or we decide different values. Why? Because you have to decide 0 here because you only see your own input and it's 0. You have to decide 1 here, what P1 has to decide 1 here because it only sees its own input. And here, if you have a connected chain of these states, to swap from 0 to 1, you need to, at some point, to change from 0 to 1 on vice versa. And actually, you have to change an odd number of times if you go from this point to this point. And for us to violate the properties of consensus, it's enough to change once. And if you change once, it means that there is a run in which you decide different values. Okay? So far, so good? Okay, so that is, in a few slides, the proof of impossibility of consensus, which Rachid has presented operationally, yeah, by constructing explicitly the executions in which you violate consensus. Of course, I cheat a little bit because I used a slightly different model of computation, but I will say a few words about this if I have time. Okay? Okay, so now, if you have more processes, what happens? And by the way, coming back to the question of scheduler, if the scheduler is not completely asynchronous, completely unfair, so it can fail some processes and let some other processes take infinitely many steps. If you take out just a single interval here, say, okay, this particular execution is not allowed by the scheduler, then you have a solution to consensus. Because you can, once you disconnect these two endpoints, you can let everybody on the left from this gap to decide the value of P0, and everybody on the right to decide the value of P1. And you have a consensus protocol. Okay, so it's inherently important that your scheduler is completely out of control. Okay? So more processes. What happens with more processes? And for more processes, I need to change a little bit the model of computation because, again, I have more processes, you have more means of communication. So now what I use is a snapshot object. Yeah, every process writes a value in its own position in a snapshot object. Remember, it's like an array of registers, which allows you to atomically read the call content in one operation. Like you have the one atomic operation which takes a snapshot of the whole array. Yeah. So this is what I'm going to use. So the one round of this model, I call it immediate snapshot because it's slightly stronger than atomic snapshot. We don't have time to really go into this, but it's something which is implementable in read-write. That's the most important thing. So okay, so yeah, I update and then I take a snapshot. This is my new view. By taking a snapshot, I get a set of values which other processes have written. Okay, so this is my new state. And if I run it more and more rounds, in every next round, I write what I learned so far in a complete fashion in the snapshot object, and then if I take a snapshot, I have a set of sets and so on. So it's what they call full information protocol. So I don't lose information. I always write everything I know. And this is important. Well, this is helpful for impossibility results, because you can say, oh, by running, if you cannot solve the problem using a full information protocol, of course you cannot solve it using any restriction of it. Okay. Initial state, now you change the dimension. Yeah, so the initial state is a simplex of dimension of the number of processes minus 1. So here we have 3 processes, and this is 2 simplex. Yeah, this is my initial state. Every vertex is colored. Yeah, the color red is assigned to process P0, white to P1, blue to P2. Okay. One round of this model. I'm not going to prove why it did the case, but if you think about it, if you look, this is the structure of one round of this media snapshot model. If you look at the boundary, you see, take any one boundary of this simplex, yeah, for example, this one, P0, P1. This is exactly what we saw before. You have 3 intervals in which P0 and P1 only see each other. They don't see P2. P2 came later and was not noticed by P0 and P1. Okay, so this is subdivision which we already saw, where respectively if P0 and P2 run fast before P1 joins, they see this, and P2, P1 identically. And in between, well, in the middle of this subdivision, we see vertices which correspond to the situations when they see everybody. Yeah, so this, for example, P1 here, he sees everybody. He sees the value of P0, value of P1, value of P2. Okay? And respectively, you have these connected things like these are all the states which are possible by running this protocol. And people prove that this actually indeed captures this model of computation, and it's called something which is called standard chromatic subdivision. It's a type of subdivision which was used in other contexts. Okay, so this is what we have. Yeah, so it's just I modeled all possible states reachable by one round of this protocol. Okay, so every triangle here, every simplex, 2 simplex here corresponds to one run of this algorithm, just one round. But the beauty of this, of course, if I run it for more rounds, I have a more fine-grained subdivision of this type. Every triangle I subdivide in exactly the same fashion. Yeah, so, for example, if I run one more round, I have something scary like this. It's scary, but it's still a subdivision, and it's very well structured. Yeah, every triangle here has exactly the same structure as the original one. Okay. And I maintain colors, yeah, of course, yeah. If you see, for example, this boundary here is like what we saw before for P0 and P1. Okay? So I have like something which is a subdivision, and by definition, the subdivision is something which preserves the geometry of the original complex. And for us, the original complex is just one simplex. Yeah, so geometrically, if you embed it in space, it has exactly the same shape. It's the same triangle. Okay? And in particular, it preserves the connectivity properties. So since originally this, let's say, n+1 processes in our system, well, again, by convention, we assume that in our system we have n+1 processes P0 to Pn, yeah, P0, P1, P2, Pn, and altogether they're n+1, and it's an n-dimensional simplex. Just to keep the nice name for dimension, we keep n+1 processes. So originally, you have like 2-dimensional simplex of 3 processes, and it was 2 connected, and it remains being 2 connected. Yeah, no matter how many rounds of this model of computation I go through. Okay? And now we can generalize consensus impossibility to set consensus. Yeah, we can say, oh, we relax the problem. We cannot solve consensus, but we want to solve some weaker problem. Yeah, for example, we have possibly n+1 inputs for n processes, but we only want to agree on k out of them. Well, agree k out of them means that everybody proposes an output. Well, everybody has an input and decides on an output, but the number of outputs, distinct outputs, is bounded by k. Yeah? So, for example, we decide what to drink tonight, and yeah, we have different proposals. 3 processes propose different values, and at the end, they choose 2 of them. Yeah, they eliminate one of the proposals. Yeah, this is an example of 2-set consensus. Okay, so starting with 3 values, we decide on 2 in total. Yeah, the outputs should be a k-bounded subset of inputs. Okay, so we never output something which was not proposed. Yeah, so this is important for consensus also. Yeah, and this is two-set consensus, and of course one set consensus is what we know is consensus, and what we know is n-set consensus in the system of n+1 processes is what we just call set consensus. I use set agreement sometimes, set consensus. Okay, and this is the problem we want to prove to be impossible to solve in a weight-free way. Set consensus. So having n+1 inputs eliminate just one of them. Okay. And this is one of the most celebrated results, and it was independently obtained by 3 groups of researchers, by Borovsky and Gaffney, Herrlich and Shavit, Zaks and Zakharoglu. In the same year, they published it in 2 different conferences, Potsy and Stock, and 2 of them were actually later published as journal versions and awarded the Gödel Prize as like one of the major prizes in theoretical computer science. And the third one by Borovsky and Gaffney was given a Dijkstra Award for advances in distributed computing. So this is one of the important observations. So you cannot, it's not only about consensus, it's just about eliminating one of the inputs. It's much more general than this. Okay, so the theorem states that you have n+1 processes, and you cannot find a protocol that solves n-set consensus if you just use, well, what we call iterated immediate snapshot model, but essentially it's using read-write memory. Okay, so there's no read-write weight-free protocol solving set consensus. And then, well, the proof essentially is a reduction to what we call a Sperner lemma. Because, well, there's a famous Sperner lemma which shows that specific type of coloring of a manifold, well, in our case, a subdivided simplex, is not possible. And the Sperner lemma is a fundamental thing in mathematics in general, and it's something which is, in another form, people sometimes know it as a Brouwer's fixed point theorem. If you take a glass of water and shake it and wait until it calms down, at least one molecule stays in exactly the same place where it was before. Yeah, if you map a space on itself, there must be a fixed point. Okay, and surprisingly, it's another formulation is a Sperner lemma. So what is a Sperner lemma? Let me see. Okay, so first of all, what's Sperner coloring? Yeah, if you take a subdivision, yeah, so you have an original simplex, and you subdivide it somehow, no matter how, and you want to give colors to it. So first of all, you color the corners. So the corners should have distinct colors, necessarily. So in our case, it's just the process identifiers. So if you only see yourself, you decide on your own input. Okay? Edges, yeah, so the one-dimensional boundaries of the simplex should have colors of the corresponding corners. Yeah, if you fall on the edge like white-blue, you should have one of the 2 colors, white and blue. In this case, we just choose blue. If you fall on this face, you should choose colors blue and red. Here you choose blue, and here red. You cannot choose white for this face. Yeah, exactly for the same reason. If you don't see white, you cannot decide its value. Okay?
Excuse me.
Yeah.
Why do you have 3 blues on the left side of the triangle?
Yeah. So now I change the semantics. It's not about process identifiers. It's the outputs. So in this case, I say, this is actually the process P0, which is white, but it chooses decision as its output value. It chooses the input of P2. Okay, so it's just for convenience. Okay, and then finally, in more generally, I just say that every vertex gets the color of its carrier face. So here, it's like the minimal face of the original simplex to which the vertex belongs. Yeah, so here, for example, the internal vertex here, it belongs to the whole simplex, and the corners of this whole simplex are all these 3 colors, so I can choose any color for the internal vertices. Well, in this case, it's not very nice because I choose only 2, but you could choose also, you could color this red, no problem, or this one, okay? So the physics of this is still the same. Yeah, you never decide on something you never seen. Yeah, so this is exactly you decide on the value you heard of. Okay, so this is so Sperner coloring is exactly what you need for set consensus. Okay, so you need to find Sperner coloring. And of course, Sperner's lemma says not possible. You cannot do this. Okay, so you necessarily you have some simplex for any Sperner coloring. You have some simplex in which you have all n+1 colors, which is prevented by the definition of set consensus. You cannot decide on all n+1 colors. You need to decide on at most n different colors. Okay? So far so good. We see that Sperner lemma is exactly what prevents us from solving set consensus. And now I just very briefly go through the proof of Sperner lemma, because, well, it's a nice proof, and I think it also entertains us a little bit. Okay. So there must be at least one run in which all n plus 1 values are decided, and the proof is by induction. So you want to prove that in any dimension. So you're actually, the usual proof technique in this domain, in the combinatorial domain for distributed computing, is by dimension, by induction on the system size. It's very easy to prove some things for dimension 1, for 2 processes, yeah, like we did for consensus. And then you can use this result for higher dimensions by inductively. So what we say, okay, for each k, the phase 0 to k, yeah, for 0 to 1, 0 to 2, 0 to 3, and so on, should have an odd number of k-dimensional simplices colored to exactly color 0 to k. Yeah, for example, if I take the phase 0, 1, and it look at all the subintervals 0, 1, 0, 1, 0, 1, I should have an odd number of vertices which have all the 2 colors, 0 and 1. Yeah, so for k equals 0, you have just one vertex. Of course, it has exactly one vertex colored, one color, so the statement is trivially true. Well, for k equals 1, this is just simple counting. You start from here. This should be colored red, 0. This should be colored white, 1. And here you go from 0 to 1, and since it's connected, you need to have odd number of switches from 0 to 1 and back. And here you have 1, 2, 3, 4, and 5. Yeah, an odd number. Okay? So simple counting shows that in one-dimensional case, indeed, you have an odd number of fully colored simplices. Okay, now I want to generalize it. So suppose that the claim holds for some n minus 1, and consider the case n. Yeah, so you want to extend the argument. And here I use a little bit of notations. Well, so this is what I have. Yeah, this is my example of a colored subdivision. So I call a room. I call just a 2-dimensional simplex in it. Yeah, and rooms can have doors. Some rooms can have no doors. It's completely inner rooms. We are not interested in this. But if you have an n minus 1 dimensional face in this room, which is colored in all colors 0 to n minus 1, it's a door. Yeah, for example, if I look at the simplices which are adjacent to this face, so I have these 3 rooms with doors. Yeah, you have 0, 1, well, 0, 1, 0, 1. So you have 3 rooms with doors. Yeah, but you also have rooms with doors inside the subdivision. Yeah. So it's just some face which is colored to colors 0 to n minus 1. Okay? We call it a door and exit if it belongs to this face. Yeah, this is something how you can get inside the apartment of multiple rooms. Okay? So now what I'm going to use, I use just a simple walking argument. So there must be some odd number of exits, and this is just by the definition, because we already use the inductive hypothesis. We know that on this face there is an odd number of processes of simplices colored 0 to n minus 1. In this case, 0, 1, 0, 1, 0, 1. Okay, so there are odd number of them. We already proved that. Okay. Okay. So we know that on the other faces you cannot have colors 0 to n minus 1. Why? Because the other faces, they just don't have some of these colors. Yeah, this is a Sperner coloring. It says that you can only use colors of the corners. You cannot use others. So there's only one face of the original simplex where you have doors. Okay, so you can get inside the apartment only through this face. So far, so good. Okay. Okay. So and since we already proved that there are on this face you have odd number of exit doors, have odd number of exit doors in total on this simplex. Okay. And now we'll zoom into one of the rooms, and let's consider a room with a door. There are 2 possible cases. Either it's a dead end, means that it only has one door. You get inside, you cannot get out of it except for using the same door, but we forbid it. Okay. Or it can be a passage, and passage means that you have exactly 2 doors. Why you have exactly 2? This is because if you already have 2 doors, it means that there is one color which repeats in one door. in one door, in the other door. And that's it. You have two possible situations. Either you go through this door or that door. Okay, so you have a passage with two doors. For example, here you have a room with a door like red, white, and red, white here. And this is dead end. You have only one door inside. And what's interesting here is the dead end is exactly what we are looking for. It's a fully colored simplex. It's a simplex which has all the n+1 colors. And in this case, 3. Yeah, this is what we want to show to exist. Okay? Okay. What I'm going to show is that there must be an odd number of dead ends, fully colored simplices. Okay. How would I show it? Well, I just use walking. I just let process enter through the door from the outside and let it walk through door to door. We know that there are finitely many simplices here. Okay? Two possible cases. Either I go through another exit door and I leave the apartment, or I end up somewhere inside in the dead end. Okay? There are odd number of exit doors. Yeah, since if I enter and go through the other one, these two cancel each other. Yeah, I remove pair of them. Yeah, I remove pair, I still left with an odd number. And then some of them, at least one of them, should end up with a dead end. Okay, so I show that from the outside world, I can reach an odd number of dead-end rooms, and this is exactly what I need. I wanted to prove that you have an odd number of fully colored simplices. Okay? Any objections? Well, I was looking for an objection because I skipped a step. What about, I only talked about dead ends which are accessible from the outside. What about the dead ends which are not accessible from the outside? But for them, I use exactly the same logic. These guys, if they're not accessible from the outside, if you start from them, you end up in another dead end. Again, you have an even number of dead ends which are not accessible from the outside, and they cancel out. So still, I'm left with dead end. The number of dead ends is odd. Okay? Okay, so okay, sorry. All right, so what we showed so far. Yeah, so this is an example, by the way. So this is two possible cases. Yeah, here you march from the exit and you end up with the fully colored simplex, or you enter here and you exit here, and that's all that's possible. Okay. Okay, so what is it? What we proved so far is actually an instance of a bigger result. And once people showed that, okay, well, set consensus is impossible, what other impossible things are there? What can we prove? And that gave rise to a characterization of this model of computations using reads and writes. This is what people call asynchronous computability theorem, which was proved, well, stated and proved a few years after this impossibility result. And it relates to proving the impossibility of solving tasks. Yeah, the set consensus is an instance of a task. Yeah, it's one specific case of a task, but in general, a task is something which can be characterized by an input complex, a set of possible input configurations, an output complex, set of possible output configurations, and the relation between them. So some specific type of a map, which we call carrier map. The details are not important. So this is something which defines the task specifications, for which input, which outputs are allowed. Okay? And the asynchronous computability theorem says that a task is weight-free, read-write solvable, using in any dimension. Yeah, so if and only if there exists a chromatic simplicial map, it's for us, for all the purposes, just a simplicial, is a continuous map from one space to another, and which are the spaces? The first one is a standard chromatic subdivision of some degree of the input complex to the output complex and should respect the task specification. It's just, I'm not going to detail it, it's just the high-level statement. Okay, so it says that it's all about subdividing the input complex. This is the only thing you can do in shared memory, in read-write shared memory. Yeah, for colorless tasks, you can even, well, colorless tasks are much simpler classes of tasks where you don't use process identifiers, you use only inputs. If, for example, set consensus is a colorless task, you can even rewrite it as a continuous map from the geometric realization of I to the geometric realization of O. Input complex to output complex. And this is because, yeah, if you talk about simple tasks like a set consensus, or simply defined tasks, not simple to prove or to solve, then you can get rid of these subdivisions because you can only talk about geometry. So this is just a Euclidean continuous map from one Euclidean space to another. Okay. The outcome of this lecture is a little bit pessimistic because what I showed is something is impossible to solve. Yeah, so we have a very basic model of computation, but we only show that it's useless. We cannot do much in this model. Okay, well, that's why people looked at in the stronger models. For example, you can talk about models with stronger objects, like you have read, write, and say test and set. What can you do? Can you generalize the model of, well, the theorem of asynchronous computability for this model? Or you have a model in which, for example, the scheduler is controlled. You exclude some executions. For example, you exclude some processes, some sets which can be faulty. You say, well, only these subsets can fail. This is what we call adversarial computing models, and this somehow excludes certain executions from the model system. Okay, and it turns out that for these cases we can actually define a pretty elegant topological combinatorial representation, which allows us to characterize the computability of this system. And this is a more or less recent result by Vito, Hey, and myself. So this is a little bit of advertisement. So this is the generalized asynchronous computability theorem, which says that a task is solvable in a model A if and only if there is a chromatic simplicial map from a subdivision of this kind. Yeah, what is this representation? It's actually what we call an affine task. It's not the whole subdivision, it's a part of it, what we call blue here. For example, for read-write system with test and set, you only can maintain these 6 executions out of the whole scope of 13, well, for 3 processes. Yeah, you only keep this. These are excluded. And you iterate it longer and longer, and this is what you get in this characterization. Okay? Just one more thing, because I think it's an interesting, just a pointer. Yeah. So you may ask, okay, we have this theorem. It says, oh, okay, the task is solvable if and only if a map exists. But can we find an algorithm that, given a task and a model of computation, shows whether there is a map or not? Yeah, just to characterize whether the task is solvable. And unfortunately, the answer is no if the dimension is 2 or more. In dimension 1, everything is easy, because basically this theorem boils down to the question of simple path connectivity. You can, given any graph, there is a simple algorithm which shows that 2 points are connected or not, or a graph is connected or not. Unfortunately, some of you might know that if you go to dimension 2 and you go to hypergraphs or 2-dimensional complexes, the question of simple connectivity is undecidable. So there's no way of devising an algorithm that, given a 2-dimensional complex, shows that a loop is constructible to a point. And because you can reduce it to what we know as a word problem in computing, so which is also known and decidable. So this was a result which actually used this particular characterization theorem, shows that actually there is a class of tasks which we call loop agreement tasks, which boil down to loop constructibility. Solving them means showing that a loop is constructible, and this is undecidable. Okay, so yet another pessimistic result, but this is life. We have to deal with it. Okay, so, but it doesn't mean that this work is useless, even though you cannot find an algorithm. Because for many cases, for many models, you can actually use this criterion very efficiently. Because well, loop agreement is a pretty exotic kind of task, which rarely arises in computing. It's just it was artificially constructed. Okay, but it's still important to understand what's possible, what's not. Okay. Okay, I put a lot of things under the rug. So what I put there, well, is it really subdivision? Well, it is. It was proved. Well, first, ironically, it was first stated, defined and claimed to be subdivision, and then proved to be subdivision. So people use it as subdivision for a while until someone came and actually proved it formally. And actually, it's funny that you can prove it either using combinatorics, or you can go and use algorithms to show that read-write is actually a subdivision. There is a very nice result by Afek and Gaffney showing that you can actually emulate a message passing model in which you naturally get a subdivision. So it's a beautiful result. Is the iterated model, which I considered in this lecture, equivalent to read-write? Well, I showed that something is impossible using iterated memory. Well, you may ask why I talk about iterations. I could talk about read-write directly. Well, fortunately, you can do this because the two models are equivalent. But it's just much nicer to represent things combinatorially in the iterative model. Okay, so for task solvability, it's exactly the same. Well, for long-lived objects, it's not. I should be careful here. But we only talked about tasks so far. Talked about consensus, set consensus. Proof of ACT, I didn't prove. Well, there is some use of Koenig's lemma at some point because I need to show that, okay, really, indeed, after a certain number of steps, you terminate, and the number of steps is bounded for every protocol. Yeah, so this is important for the using the Sperner's argumentation. Okay. What are the takeaways? I'm almost done. First of all, this language of combinatorial topology allows us to represent, well, visually sometimes even, distributed computations. So it's very appealing aesthetically also. So you can see what's going on in the system by looking at this object. You can see how the system evolves by looking at the invariance this object exposes. For example, connectivity, whether connectivity remains or maybe at some point it breaks. If it breaks, you can already reason something, say something about the complexity of the protocol, how many rounds it takes to break the connectivity, and so on. And in some sense, it's a constant debate between operational and combinatorial approaches. Operational is much more ripe. It's much more developed so far because it's been used for 40 years. Combinatorial approach is pretty young still. Well, it's still already 20 years it was proposed, but still it's far from being developed. So it's hard to compare. Much more results in the operational scope. Yeah, but still, so there are other interesting questions which are worth being considered from the combinatorial perspective. If you go beyond tasks, go to long-lived objects like online services which respond, maintain state. You can access it again and again and again. I don't know, like a vending machine here. So it maintains state and it can be accessed multiple times. It's not like a task. If you go beyond crash failures, we go to Byzantine adversaries. If a process can deviate arbitrarily from the protocol, what changes? It's very hard to model combinatorially. If you go from asynchrony, you go to partial synchrony, for example. So you have some partial synchrony in the system. It's not completely asynchronous. Can you derive some complexity bounds? It's a very appealing thing because so far we only talk about computability. We never say anything about complexity. So how expensive are these protocols? We don't know. Can we use this approach to do this? Hard to say. Mathematical structures induced by DC, so by distributed computing in general. So there are some interesting works on this and some really interesting complexes which were never observed in other branches of mathematics or in other branches of science in which mathematics, topology was applied. Yeah, so there's something unique about computing. Okay, well, in general, so the distributed computing world is something very diverse. You have a lot of models, you have a lot of perspectives. And this, I like this, it's a Chinese tale about wizards touching the elephants, and they're blind. They only touch and they only see their own, or they only understand some part of this big animal. Just to see the elephant, we need, well, maybe all these models, and I also even put this blockchain now because I think the most important, well, the most famous at least distributed system nowadays is Bitcoin. Anyway, so and people all treat it as distributed systems with completely different notions. So to merge it together, maybe they are different. They have different communication primitives, different timing assumptions, but they have the same combinatorial structures. And computationally, they could be shown equivalent, and this is something which where you can use the formalism I just presented. Okay, so about the sources of information. So there is a book which has been published already 5 years ago. It gives a very nice introduction to the field of distributed computing from the topological perspective. So by Maurice Herlihy, Dmitry Kozlov, and Sergio Rajbaum. And for more like operational perspective, I still give a little bit of advertising. So the book is not yet available online, but you can go to this Librairie Airolls, which is just next door on Boulevard Saint-Germain. And so it's already there. I checked in the underground floor, so you can find it in the Informatique Algorithmique section. And I think I will stop here. Thank you very much. And if you have questions, you can pose it in French. I can try my French to answer.